Hey everybody, here's the next problem here in this homework number 4 for machine design, ME304. This is a pressurized polypropylitic steel plate with a fracture toughness of 92 psi. Actually, I'm going to let you guys read the rest of that to get the point of what the problem is. You can go ahead and pause the video and do that. I'm going to crank right on into this. Okay, so we've got KIC, which is a fracture toughness, equal to 92 KSI square root inches. It's a weird unit, but it's the way it is. And then we're actually going to move off down here actually to the next one. Delta P is equal to 10 KSI, which is actually equal to the P peak minus the P the P valley. And this is the change in the amount of stress or the pressure that you put on the tank at any given time. So this is if you were thinking of a sine wave of the pressure going up and down, this is how you would calculate it if you actually saw that sine wave. So then we also have beta is equal to 1.3 with a crack at a crack of 0.1 inches. Oh, we're working in inches. It's so nice. So finding hours to failure. So T to fail is equal to something hours. Okay, so we're looking for, to start out, we're going to start with cycles to failure, which is the basic equation for this is NF, cycles to failure, is 1 over C, which is a constant. The integral from AI to AF of, let me move this up a little bit here, dA all over beta delta sigma square root of pi A squared, or to the m, sorry. And beta is equal to 1.3, so we have beta. We need delta sigma, and we also, we need delta sigma. So we know that delta sigma is equal to KIC over beta. Your professor should have lectured about this at one point. So that's a way to reduce. I mean, it's similar to this equation, but you can see that it's a little bit different. We're not going to derive it right now. Okay, so we can't really use this yet because we don't know what the A or the beta is, there's just nothing useful here for us. We have to find the A. That's going to be derived because this is A final. Okay, so what we're going to do is we'll use this equation later to figure some stuff out, but right now it's going to stand off to the side. But we know this is a pressurized vessel. So we're able to use a pressure vessel equations. And first of all, we need to find out if it's thick-walled or thin-walled. So we've got the R interior. R interior is actually equal to 5 inches. And then R total is equal to 6 inches. R outer. So we get Ri over R thickness, which is equal to, what is that, 5 inches over 1 inch, which is equal to 5, which is less than or equal to 20. So thick-walled. It's a thick-walled vessel. If it was thin-walled, it'd be an easy calculation, but since it's thick-walled, the professor is giving us a little more work. But that does give us the equation, because we can know delta sigma is equal to Ri squared delta P all over R outer squared minus R inner squared all over 1 plus R outer squared all over R inner squared. Close that. So then delta sigma is equal to 5 inches squared minus 10 KSI, which is delta P, all over, going ahead and subbing in and doing it after this. This is 36 minus 25. The algebra is kind of scattered here, but you guys can figure it out. You're supposed to work it yourself anyway. 6 squared all over 5 squared, which is equal to, let me move this down here. So delta sigma is equal to 22.72 times 2.44. You do all that math. So delta sigma is equal to 55.44 KSI, which we will use here in a little bit. Now, using this equation up here, we still need to find AF. AF is equal to 1 over pi KIC all over beta delta sigma squared. And you guys can all see kind of how it came to be. So, solving for that is equal to 1 over pi of 92 ksi all over 1.3, which is beta, which we saw earlier, times 55.44 ksi squared. And then solving that out, you get AF is equal to 0.5186 inches. So this is the final size of the crack when failure will occur. That's what this value is. So we've got the A initial up here of a 0.01, and then we've got A final of half an inch where everything breaks, and we have complete failure of the vessel. So we've got AF, we've got delta sigma, so we can move on to the next equation and actually figure this out here. So moving on, I'll try to set this off to the side. Maybe you guys will be able to see some chunk of it. But so going back to our original equation of NF is equal to, okay, little thing. This equation, beta is a constant. This is now a constant. A is a constant. Pi is a constant. Well, no. Well, A is not a constant. It is a changing value going from 0.01 to 0.51 stuff. So the A is going to be the value that we integrate from AI to AF. So, and M is actually going to be something we look up in a table, as is C. So we're going to rearrange this equation. I'm going to show you the rearranged value right here without showing any of the algebra, because that's an easier thing to do. Alrighty, so NF is equal to 1 over C times beta delta sigma square root of pi, the power of m, integral from AI to AF of a to the negative m over 2 dA. If you did all the algebra to reduce this integral, you would have found this out. But we don't. I don't want to spend time on that right now. Which is then equal to 1 over 1 minus m2. This is actually after having done the integral also, times c times beta. Moving on, doing this integral with just the variables here. Beta delta sigma square root of pi, power of m, carry that on out, all times a final 1 minus m over 2 minus a initial 1 minus m over 2. So that's doing the integration just with the symbology there. And now you know what the basic equation is. We have an algebraic equation. All we have to do is solve this, and we'll get the number of cycles to failure. And we know that the number of cycles in hertz, and that's 1 cycle per second. So we'll be able to transfer this directly into seconds and then convert it into hours. So it's really easy. But we still need C and we need M. So looking at table 6.-1 in your book, you'll find that C is equal to 3.6 times 10 to the negative 10th, and M is equal to 3.00. And this is table 6.1 back in the appendix, I believe. No, it's not in the appendix. It's in the chapter of the Shigley machine design book. Okay, so this is then equal to 1 over huge amount of stuff. So 1 minus 3 halves, which is m, 3 over 2, times 3.6 times 10 to the negative 10th, which is c, times beta, which is 1.3 times 55.44 ksi, which is the value we calculated earlier, times square root of pi to the power of 3, all times a final, which is 0.516, 1 minus 3 halves. I'm actually going to have to move this stuff up. Sorry. I'll write it back down here in a second. Minus 0.01, which is the initial, to 1 minus 3 halves. This is inches, this is inches. Moving in on that. I'm actually going to write this table back down here again. So go ahead and skip ahead like 30 seconds. You don't want to watch me write this again, which is 3.6 times 10 to the negative 10th. 10 is equal to 3.00. Okay, so moving on like that. This all yields negative 266.5.04 of 1.392 minus 10, which is equal to negative 8.61. So then NF is equal to 22,945.99 cycles. So we've got cycles, which is basically equivalent to seconds because of hertz. So each one of these cycles happens in a second. So we've got NF seconds. And then if you want to go through the conversion, 1 minute over 60 seconds, and then 1 hour over 60 minutes. And this will cancel, and this will cancel with that. And then you just sub this value right on in, and you find out that 22,945.99 divided by 60 times 60, which is equal to T final in hours, is equal to 6.37 hours to failure, which is not a very long time, but is what it is. So that's your answer. That's how long this thing can cycle before going into failure. So ways to fix that would just reduce the number of cycles or make a thicker wall. There's all kinds of stuff mechanically that you can do to fix this problem. But that's what we get for this problem.